Alright, Prop 35 says parallelograms which are on the same base and in the same parallels are equal to one another. So a couple of comments that I want to make before we jump into this. On the one hand, what is this even saying? So it's saying if you imagine there being sort of some parallel lines, and I guess I should also note that I've made two different diagrams, and I'll explain why I made two different diagrams for this. But the setup is if you imagine there being a pair of parallel lines, and then between those parallel lines are parallelograms where they have the exact same base, but maybe the top is not exactly the same. Then the claim is that the areas of these two parallelograms are equal to each other. So maybe that's the first thing that I'll point out, is that previously when we talked about two figures being equal, like two triangles being equal, we meant that they were congruent. And that's no longer how we are referring to that here. We don't mean that the two parallelograms are congruent, we mean that they have equal areas. And that's pretty intuitive when you think about it, because we know that taking the area of a parallelogram, you would multiply base times height. So we're saying here, well, we've got two different parallelograms, one that is the solid line parallelogram and then the other that is the dotted line parallelogram. They both have the same base, and then they fall between the same parallels, so their height is always going to be the same. So from that sort of perspective, it becomes a little bit more obvious than maybe it is at face value. Let's see, what else was I going to say? Right. So I made two different diagrams because one of these diagrams is actually the more general case. The other diagram is, I think, the diagram that you would think of maybe more readily, or at least for me, it's the one that comes to mind more readily, which is the left case. So when I was first going through this proof, and I kind of drew up my own diagram without looking first at the diagram they drew, this was the diagram that I drew. And I started going through it, but Euclid uses sort of this case, this second case here, which is, as it turns out, the more general case. So he proves for the second case over here, but I wanted to put this over here as well, because if you're like me and you draw this diagram and then you're following along through the proof, there's sort of one spot in the proof where the proof doesn't actually apply to this and it can be simplified. So yeah, this is the more complicated diagram. Sorry, this is the simpler one. This is the more complicated one, but it's also the more general diagram. So what is the main difference? Well, on the left, the main difference is that BE, this line BE, doesn't ever intersect the line DC. And this is kind of like without loss of generality. It could be different lines, but up to reordering, it's the same thing. So case one is the case where BE intersect DC is the empty set. Case two is where BE does intersect DC at some point. BE intersects DC, and we'll call that point G. And all of this, by the way, is just sort of left out of Euclid's proof. He doesn't really kind of like state all of that. He just sort of assumes that like you can look at the diagram and figure out what G is and how G comes about. But in any case, these are the two different cases. If we prove this right case, it proves the same thing for the left case, because this is sort of the case where the idea is that this right case forms this little triangle DGE in here. The left case is sort of like where DGE is the trivial triangle that it had with zero area. So it still works. The Euclid's proof works for both of the cases, but again, just if you're kind of running through this on your own, I thought that I would maybe make two different diagrams. Alright, so right, in either case, and I guess I'll mostly point at the right diagram here. I'll just mention the left diagram when I get to the point where I'm like, this is where the proof doesn't really apply to the left diagram. In either case, assume that we have two parallelograms, ABCD and EBCF, where they share a common base, BC, and they both lie between the same parallels, meaning sort of like the side that is opposite the base that side lies on the same line. Okay, and then what we want to prove again is not that ABCD is congruent to EBCF. We want to prove that they have the same area. And again, I think it's kind of like interesting because that isn't really made explicit, and in these propositions, at least previously, when we talked about two figures being equal, we normally talked about them being congruent. Now we're going to kind of switch up and talk about areas being equal. And of course, if triangles are congruent, then their areas are equal, so it's sort of implied, but there is using the term two figures being equal, it gets a little bit overloaded. So here we're talking about area. All right. Okay, so how do we do this? Well, since ABCD is a parallelogram, we know that AD is equal to BC. So AD is equal to BC. We had a proposition that told us that. It was proposition 34. Said that opposite sides of a parallelogram are equal to one another. For the same reason, EF equals BC. Same proposition gives us that. So, by common notion 1, we would have that AD is equal to EF. Right. So after he states this, and this is a proof where there are a number of things that are kind of left out. That's sort of why the first 5 minutes of this video, I was just talking about some of like the setup here. There's a lot that he kind of leaves out that I think should be added in. After he states both of these pieces and he concludes that AD equals EF, what he says is, and DE is common, therefore the whole AE is equal to the whole DF. So I'll just write that. So AE equals DF. And I want to kind of fill in the blanks there. And depending on the diagram that you're using, actually filling in the blanks is slightly different. So with, and I guess I'll call this maybe case 1 and case 2. So with case 1, how do we arrive at AE? So we're saying AE equals DF. Well, it's because we could note that the whole top piece, DE, is equal to AD plus AE. But we could also rewrite it, DE is also equal to EF plus FD. And based off of what we just found, that AE equals DF, sort of like just looking at this right piece, this equality right here, since AE equals DF, we conclude that AD equals EF. Sorry, AE equals... Okay, I'm getting all confused here. So looking at this piece, what we had was AD equals EF, sorry, and that's the piece that we're subtracting off to get this conclusion that AE equals DF. Yeah, that's what we wanted. So that's how we prove it in diagram 1. Diagram 2, it's still true, it's just that proving it is a little bit different. So we know that AD equals EF again. And this is more how Euclid does it, because when he says AE equals DF, he cites common notion 2, which is the one that says equals added to equals are equal. So from AD equals EF, if we add in the common line DE, we get to both sides AD plus DE equals EF plus DE, but AD plus DE is really just AE. And EF plus DE is really just DF. So that's how that line is justified. This was common notion 2, and that's that only works here. So this is common notion 2. I think that with this one it would be, this might be more common notion 3 for diagram 1, since you're subtracting, right? Yeah, pretty sure. Okie dokie. What's next? So yeah, AE equals DF. So, but notice what we have. Then we have, so he says, but AB is also equal to DC. Have we said that yet? No, we haven't, but we can prove that. Then we have that AB equals DC, yep. And that comes again from Prop 34. Opposite sides of a parallelogram. So AB equals DC. We also have that EA, or AE, yeah, equals DF. Yep. And we have one last thing, which is the correspondence of angles. So far, right, looking at this right-hand diagram, we have AB equal to DC. We have AE equal to DF. So just kind of looking here, we were looking at AB and AD. Next we'll look at this angle right in here. So we also have that angle, and he states it as EAB, I believe. Yeah. Yep. Angle EAB is equal to FDC. And why is that true? Well, that comes from Prop 29. So the idea is that AB is parallel to DC with this sort of top line cutting through them. So since these two lines are parallel, this angle right here is going to be the same. So that's where we get this piece. And from these together we have side, angle, side. So triangle EAB equals triangle FDC. And that was Prop 4 with the side, angle, side. Yep. Right, and here is the place where the proof for the two diagrams kind of gets different. Because if you're looking at just the left diagram, what we've shown is that this triangle is equal to this triangle. So what I'll do is I'll just say for diagram 1, add the quadrilateral A, B, C, F to each. Yeah, and then note that the original parallelogram ABCD is equal to this quadrilateral ABCF plus DFC or FDC. So ABCD is equal to ABCF plus triangle FDC, which is equal to ABCF plus FDC is equal to EAB, but ABCF plus EAB is parallelogram EBCF, which is what we needed to prove, that those two parallelograms are equal. So for case 1, that's all we need to do to finish it out. But case 1 is like a specific case. Case 2 is the general case. So, and this is the reason that I pointed this out, is because if you're looking at case 1, this next statement comes out of nowhere and it seems kind of strange. So he says, right, we said EAB is equal to FDC. So in the left diagram, EAB, so this triangle, is equal to FDC. And he says let DGE, the triangle, be subtracted. from each. So from each of these triangles, we're just taking off this tiny little triangle DGE, which leaves us with strange quadrilaterals. He calls them trapezium. So like EAB, once you subtract off DGE, we're left with ABGD. Then ABGD is equal to, and again, same thing over here, when we subtract off from FDC, if we subtract off DGE, we're left with this trapezium EGCF, right? Is that it? Yep. So EGCF. So we subtracted equals from equals, so we have that these two strange trapezium are equal, which is interesting because they don't actually look the same at all. So ABGD equals EGCF. That was just common notion 3. And then add a triangle GBC to each. So GBC is like sort of this intersection between the two parallelograms. So, and we're going to add that to each. But notice that we have that ABCD is equal to ABGD, so the trapezium, plus GBC. And ABGD is equal to EGCF plus GBC, and EGCF plus GBC is parallelogram EBCF. And again, that's what we wanted to prove. So this chain of equalities shows that ABCD equals EBCF, which is what we wanted to prove. So the parallelograms are equal. QED, therefore, etc.